Okay, morning everybody. So let me remind you about what we saw yesterday. So what we did yesterday was take some non-abelian gauge theories, UN gauge theories, with a bunch of objects in the fundamental representation, scalar fields in the fundamental representation. We pushed the theory into the Higgs phase by turning on a Phi-Leopolds parameter. This was the V squared in the theory. And then the theory admits vortices. So the vortices were infinitely long string-type objects. And we looked at the low energy dynamics of the vortices, and I showed you how the low energy dynamics was the CP n-1 sigma model. Okay, they were the orientational modes of the vortex string. Okay, so what we've got now, using this vortex string, is a map from this particular four-dimensional gauge theory, UN with NF equals NC flavors, to the CP n-1 sigma. So now we can start playing the following game. We can ask what happens if we change the four-dimensional theory. What happens to the dynamics of the vortex string? So, for example, we could add extra fields. We could add extra scalar fields, extra fermion fields. We could add extra interactions between these fields, some Yukawa couplings, maybe some potentials for the scalars. We could start introducing vacuum expectation values for some of the scalars. And for all of these deformations of the four-dimensional theory, we can ask, how does the two-dimensional theory react? Sometimes the string will get more zero modes, so there'll be more fields living on the world sheet of the string. Sometimes it will induce different interactions on the string, maybe induce potentials on the string, and so on. So by playing this game, continually adding extra stuff in four dimensions, we end up with a rather rich map between a whole class of four-dimensional theories and a whole class of two-dimensional sigma models or variants of sigma models that live on the string world sheet. Okay, so what the vortex has done for us is provide us with a map between four-dimensional non-abelian gauge theories and two-dimensional CPN sigma. So now comes the interesting thing. And the interesting thing is that in certain situations, the quantum effects of the four-dimensional theory and the two-dimensional theory coincide. So what this means is you can do calculations in a two-dimensional theory, which is a hell of a lot easier than doing calculations in a four-dimensional theory, and extract exact results about the quantum effects of that four-dimensional, strongly coupled non-abelian gauge theory. Okay. So what I'm going to do in this lecture is explain how that works in the simplest situation, and the simplest situation is when you have n equals 2 supersymmetry in four dimensions, and a whole slew of things are known about the four-dimensional theory by using the Seiberg-Witten solution. Okay, so the plan is, to begin with, I'm just going to spend 10 minutes telling you what Seiberg and Witten did. I'm not going to explain the whole solution to you. That will take a whole series of lectures in itself. In fact, there were lectures at TASI in maybe '96. I guess you missed them. by Michael Peskin. They're on the web. Say again? Okay, so let me just tell you what Seiberg and Witten did. Yeah, sure. So certainly the way it works in the cases where you have supersymmetry is that there's actually a beautiful matching between n equals 2 supersymmetry in four dimensions and 2-2 supersymmetry in two dimensions. If you write down all the possible deformations that you can break an n equals 2 theory to an n equals 1 theory, there's a one-to-one match between those deformations that break a 2-2 theory to a 0-2 theory. So at least at the level of supersymmetry, you don't have any extra degrees of freedom on either side. There's really a one-to-one map between all the different objects you could add. Superpotential terms essentially on one side, 0-2 superpotential terms on the other side. You don't look convinced by this answer. Sorry, I didn't hear. Say again.
I'm just still a little confused about what experience you get from higher I guess that turns into a function.
Well, you have a higher dimensional Lorentz invariance, but you have a very different field theory as well. A gauge theory versus a sigma model. I'm not sure I understand the question, so let me give you the example, and then we can come back and discuss how it works. Okay, so let me just recall for the n equals 2 theories, I'll take a UNC gauge theory plus a number of fundamental flavors. And as I mentioned yesterday, I'll take the number of fundamental flavors equal to the number of colors. Okay, and this is just for Eva. Okay. I'll explain the joke later if people don't get it. Okay, so this is the Lagrangian, or at least the bosonic part of the Lagrangian for theories with n equals 2 supersymmetry in 4 dimensions. There's a Yang-Mills term. This is the complex adjoint scalar that sits in the vector multiplet. Then we're going to have a bunch of hypermultiplets. There's nf of them, but remember nf is equal to nc. And throughout this lecture, I'll usually just call it n. So each hypermultiplet comes with two complex scalars. There's a q and a q tilde. One's in the fundamental, one's in the anti-fundamental. Then there's coupling terms between the A and the hypermultiplets. Like this. And then there's some D terms and F terms. There's implicit sums over the flavors in all of these. And as I said, stressed yesterday, this is an n by n matrix. This. And then there's a bunch of fermions, which will play an important role by giving fermion zero modes to the vortex worldsheet, but for the most part, I'll leave it easy. Okay, so what did Seiberg and Witten do? Well, Seiberg and Witten essentially gave us the low energy solution for long wavelength physics in this theory on the Coulomb branch. Okay, so let me explain what that means. So the Seiberg-Witten solution, which is now way over a decade old, is valid when you set the vevs of the fundamental fields to 0. You turn on vevs for the adjoint scalar, A, because A and A dagger have this commutator term in the potential. You have to make them diagonal. And what this does is it breaks the gauge group down to a bunch of U1s. Okay, so what do we have? We have what's called the Coulomb branch. So this is the space of all vacuum. So this is the space of all possible A's up to the permutation symmetry that you get from the Weyl, that's left unbroken by the Higgs. Okay, so what do they do? Well, this theory doesn't confine. What you have at low energies is precisely these U1 photons that are floating around. So what they do for you is, as a function of these vacuum expectation values, that means at every single point on the Coulomb branch here, they firstly tell you what the interaction terms are between these low energy photons. Okay? Now at any given point, that's really just a number. It's not that impressive. Or maybe it's quite impressive. It's kind of like calculating f pi in the chiral Lagrangian from first principles in QCD. But what they really do, and what is impressive, is to understand that one should view this as a function over this manifold. So you should view this whole slew of theories as, well, sort of in its entirety. Okay, so the first thing they do is the interaction terms for the U1 photons. Okay, let me just stress here that when you're far out on the Higgs branch, where far out is defined by the strong coupling scale and the QCD of this theory, it should really be the difference of eigenvalues rather than the eigenvalues. Then everything is weakly coupled. Then the Higgs mechanism kicks in before the non-abelian theory has a chance to go strongly coupled. So this is decoupling. So there everything is essentially classical. plus one loop correction plus semi-classical effect. What's much more interesting is this region in here, where everything's strongly coupled and all bets are off. You need to be much smarter to figure out what's going on. I should also say this is a bit schematic. In gauge theories, U3 and above, the strong coupling region also stretches to infinity because you have places where, say, an SU2 subgroup remains unbroken. Let me neglect that. Okay, the next thing that they compute using their solution is the exact BPS mass spectrum. And this is really what I'm going to focus on in this talk. So what does that mean? It means that, as a function of these parameters AI, they can tell you the mass of the W boson, the mass of the quarks, that's the Q and the Q tilde fields, and most importantly, the mass of the magnetic monopoles. Okay, so let me tell you a little bit about the magnetic monopoles. We have a breaking here where the UN gauge group is broken down to the Cartan subalgebra, a bunch of U1s. So there are classical solutions of this theory, which are Toft-Polyakov monopoles, which at large distances look just like a Dirac monopole. That means they carry magnetic charges in these various U1s. Okay? So we saw the Dirac monopole in a very different context in lecture 2, in Berry's phase. But here it's really a monopole that carries magnetic charge under electromagnetism in some abstract space. Whereas the Dirac monopole is singular as you go into the origin, the Toft-Polyakov monopole here is nice and smooth because as you enter the center of this object, the non-abelian gauge fields start to get turned on and smooth out these singularities. So there's these Toft-Polyakov monopoles. And I'm not going to give you too many details about them. For those that are interested, the TASI notes I gave 2 years ago that I've handed out 2 chapters on, they contain a chapter on magnetic monopoles. What you really need to know for the purpose of this lecture is the classical mass of this solution. So this is the Soliton solution. It's a configuration in field space. You integrate the energy over field space, and what you find is that the mass is 4 pi over E squared times the vacuum expectation value of the A's. So I've been a little imprecise here again, really. It's things like one AI minus another HA that sits in there. Okay, so this is what they tell you. And the real key physics in the Seiberg-Witten solution is captured at special points in this manifold, all of the interesting ones of which sit in a strongly coupled regime, where some of these extra states, the W bosons, the quarks, the magnetic monopoles, become massless. Okay? So these are singularities in the Seiberg-Witten solution. The Seiberg-Witten solution tells you how the U1 photons are interacting, but when you hit these special points, some other light states are coming down, and you're asking the wrong question because you're neglecting these new light states. Now the situation is exactly the same as with Berry's phase. Even when you're way out here, where these light states aren't important, it's the fact that they're becoming massless which is actually determining the whole solution over this space. So it was by figuring out which singularities sit here, together with some ideas about electromagnetic duality, that Seiberg and Witten were able to understand the solution for the low energy physics everywhere. So remember, it's just like Berry's phase. The existence of the singularity at the origin there determined the physics even when you stayed way clear of it. And it's exactly the same. Okay, so let me tell you what these singularities involve. So which states become massless? Well, you might think, it's kind of obvious. You know, this W boson is going to become massless as soon as these AIs go to 0, or as soon as they become equal, then the Higgs mechanism isn't working completely. You get some non-abelian gauge group left, and that's telling you that the W boson is going up to 0. That doesn't happen, at least not in the most naive theories or simple theories that you can write down. The reason is the way you think that's happening is in a strongly coupled regime, and you can't trust your classical intuition at all. So what Seiberg and Witten found that was really very surprising is that the objects that become massless are these guys here, these big heavy solitons which at weak coupling with small e squared are really much heavier than the perturbative states. At strong coupling, they're the guys that become elementary particles and massless. So there's a number of singularities somewhere in this strongly coupled regime where monopoles and typically dions as well, they're monopoles that also carry a bit of electric charge, become massless. Okay, so they know the mass of the monopole everywhere, and it's a few points where these monopole ions. Okay, so that's one thing that I want to stress about the Seiberg-Witten solution. The second point that I want to tell you is that amongst the singularities, and typically these singularities are actually some codimension, they're not just points, they're some codimension within this space. There are further special points where not just a monopole becomes massless, but one of these quarks or W bosons also becomes massless. So here you have an object both with magnetic charge becoming massless and with electric charge becoming massless. So that's kind of a strange situation. For example, it's very much like a Lagrangian description of very light particles with both magnetic and electric charges. So what's going on here? Well, what is going on when these two states with both electric and one state with electric charge and one state with magnetic charge both become massless is you get some typically strongly interacting superconformal field theory. There are special points where M mono and say M quark equals 0, and these are superconformal field theories that go by the name of RG Douglas points. Okay, so there's a whole nice story that goes with these superconformal field theories, and the classification of superconformal field theories with 8 supercharges has one of these rather famous ADE type structures. And there's enough known about them so you can compute the dimensions of all chiral primary operators. The fact that there's an ADE structure to this will come back later in the talk, because there's something similar for minimal models in 2 dimensions, and we're going to make the map between them. Okay, so that's my whirlwind description of the Seiberg-Witten solution, or at least what Seiberg-Witten allow you to compute. So are there any questions about this before I go on to vortices? What happened? Okay, so what on earth has this got to do with vortices? Well, there's an obvious problem here, which I guess is why back in the mid-90s nobody thought that vortices had anything to do with Seiberg-Witten theory, which is that Seiberg-Witten theory doesn't have vortices. Okay, what's going on? What's going on is that to get vortices, remember we needed to break the gauge group completely. That's what, say, the abelian Higgs model does. U1 gets broken completely. Here all the U1s are surviving still. So there's just not the topology to support any winding number of vortices. So to get vortices, we can't work with this theory. We have to deform this theory in some particular way. Okay, so problem 1 is that there are no vortices. And the resolution is that we're going to introduce a Phi-Leopolis parameter. The Phi-Leopolis parameter was the V squared that sat inside this D term in the potential. So this is the new guy we've introduced. Okay, very good. We put in a V squared. Now we're essentially back to the theory we were talking about yesterday. There's vortices, but why on earth would it have anything to do with the Seiberg-Witten solution, which is valid over this Coulomb branch when V squared is equal to 0? Okay, so let me give you a couple of answers to this. One of which is glib and cute, but kind of wrong, and the other one is a little more accurate. Okay, so the question is, why would vortices which require necessarily v squared to be non-zero know about the Seiberg-Witten solution with v squared equals 0? Okay, they're just two completely different theories. The physics is way different. So there's two answers. The real answer is that what we're computing is things that are insensitive to the ratio of v squared over lambda QCD. So I'll try and make this a little more specific later. But typically what this means is things that are protected by supersymmetry. You know, the things that are protected by supersymmetry are f terms. They don't depend on d terms. Phi-Leopolis parameter here is a d term. So roughly speaking, that's what's going on. Like I said, there's a slightly more glib explanation that I like to give, even though it's not really correct, which is that take the vortex string here. Okay, outside the vortex string, q squared is equal to v squared. But we saw yesterday that when you go into the core of the vortex string, the q field drops to 0. So inside the core of the vortex string, the vortex string should somehow know about the full non-abelian gauge dynamics. Okay, the core of the vortex string is the normal state, and the normal state is the non-abelian gauge dynamics. Okay. So that's kind of a cute heuristic picture. Okay. So what do we have? This is the potential. This is the d term, this is the f term, and then I said there's the ones that I just rubbed off the board there. QI dagger. So now we have a second problem. So we've turned on a v squared, we've deformed our theory, but nonetheless we have reason to hope that the vortex string is going to know something about the original Seiberg-Witten solution of v squared equals 0. But now comes the second problem, which is that the vacuum of this theory, well, by turning on v squared, I've necessarily had to turn on q. So remember, this was the solution we had yesterday, where a is the color index, and I is the flavor index. Q tilde, you just said equal to 0. But now when this turns on to cancel the v squared, so this is 0. So it's this that turns on to cancel the v squared, so this is 0. This is automatically 0 because q tilde is 0. But now we've got to worry about these guys. And because we've turned on the q's, we can't turn on the a without raising the potential energy. So the vacuum solution has to have a equals 0. But it's kind of a problem because the Seiberg-Witten solution was all about understanding how physics changes as you vary a. And here you see that once you turn on v squared, you're stuck at the origin of the Coulomb. So how are we going to get around this? Well, so the problem is, how do we explore the Coulomb branch, meaning non-zero a's, through the vortex string? Okay, and here's the answer. The answer is what we're going to do is introduce masses to the hypermultiplex. So given n equals 2 supersymmetry, the Seiberg-Witten theory, there's essentially just two deformations you can do that preserve n equals 2 supersymmetry. One of them is turn on a Phi-Leopolis parameter, and one of them is turn on masses for the hypermultiplex. So I'm going to do both. So you give masses to q and q tilde. And the way the masses come up is that qi dagger is that the physical masses that these objects get isn't the mass m that you give it, it's the VEV of A, the Coulomb branch scalar, or the adjoint scalar, minus m. Okay? So this is the way that supersymmetry dictates that the masses sit in an n equals 2 theory. What this means is that if we want to turn on a Q to cancel this Phi-Heliopolis parameter, we've got to turn on an A. That's equal to the masses to give a 0 here to allow the Q's to turn on. Okay? So this is the vacuum of the theory. You've now turned Okay, so a little caveat here. The Seiberg-Witten solution, they give you the solution for all values of m, and for a fixed value of m, for all possible values of the scalar field A. If you want to understand what the vortex can see, it can't see all of this. It can just see some subset where when you vary A, you vary m as well. Okay, so I can't get everything. This is the subset of the Coulomb branch that I'm going to see from the vortex strip. So we explore some subset of the Coulomb branch where the A is equal to the m. Nonetheless, this is general enough to see all of the phenomena that Seiberg would taught us exist. Okay, are there any questions? Okay, so now we have a slightly different theory from the one I told you yesterday. The one I told you yesterday had the Q fields, but didn't have the A fields here. And we saw that the moduli space of the vortex string was CPN. Okay? And the CPN came from the orientation modes of the vortex string. That was how the vortex is embedded in the UN gauge group. When we have an A, but we set A equals to 0, it's going to be exactly the same story because A is 0 and not playing a role. But now we've got a slightly different setup. We've got a new field A, and A is getting a vacuum expectation pattern. So what we need to ask is the question, how is the theory on the vortex string, this CPN sigma model, affected by the presence of this masses? How does it respond? And you can see that actually it's going to have kind of a big effect. The way we got CPN was to take a vortex, put it in the top left-hand corner of a matrix, and then rotate it anywhere else we wanted in the matrix by using the SUN gauge group action and flavor group action. But when A is turned on, we no longer have that gauge group action in order to rotate the vortex into other parts of the matrix. Okay, it's been broken to a bunch of U1s. So we expect that the presence of the masses is going to change the low-energy dynamics drastically and change this CPN manifold to something else. So let's see how that works. So, how do masses affect the vortex? So recall previously we had this CPN minus 1 sigma model, and I had this picture where there's a vortex which, again, can fluctuate backwards and forwards, but that's kind of trivial. All the interesting physics is in what I called spin waves. So you see, as you go along the vortex, at every single point, I have to tell you the orientation of the vortex within the gauge group. You can denote that by a little arrow which points somewhere in this CPN minus 1 manifold. And as you move along the vortex, that arrow can slowly change at arbitrarily long wavelengths because these were massless moduli on the vortex. Okay. But now the UN gauge group is broken. We can't sweep out full CPN minus 1 space of solutions. Okay, so what happens? Well, it's not hard to see. The only vortex solutions that survive are those which, when evaluated on this term here, which is the new term that's causing us problems, give 0. Okay? So this new term here could possibly raise the energy of a vortex, and if it does raise the energy of a vortex, it's no longer a solution. So the solutions are the ones which vanish when evaluated on this term here. And it's really fairly easy to see. The solutions that survive are diagonal in the gauge group. I.e., the magnetic field, which is an n by n matrix, has to be of the following form. The U1 vortex gets embedded in one of the diagonal elements of this matrix. Okay, so just to reiterate the point again, before we put it, say, in the top left-hand corner, and then using this SUN symmetry, we could sweep it out anywhere we want it, so it goes into these off-diagonal points. We no longer have that SUN symmetry. It's broken. So the only solutions that survive are the n different vortices embedded in the diagonal. Okay. Okay, so before we had this moduli space of solutions where this vector could take any point it likes on CPN. Now what we're left with are n isolated solutions. That is that there's n distinguished points on this CPN that are left as solutions, and everything else is no longer a solution. So in terms of these arrows, you could think of the only solutions being all the arrows pointing in the same direction. And then there's n-1 other directions that they could point in. So for example, for U2, this picture would correspond to B equals sitting in the top left-hand corner. This picture would correspond to B sitting in the bottom right-hand corner. No other possible solutions. Okay, so how are we going to capture this from the perspective of the vortex string theory? That is, what's the model I write down that describes this? Okay. So, the vortex theory is okay, this was the CPN model. Remember, this was a Lagrange multiplier that imposed a particular constraint. And there's this important formula, which is that the size of the CPN is given by 2 pi over E squared, where E squared is the gauge coupling constant. The gauge field in here, remember, is just auxiliary. It's there to tell you that if you rotate all the phases of phi by the same amount, that's to be considered a gauge transformation, and you identify those configurations. And that, together with this, gives CPN. So what I do is I introduce another auxiliary field. So this is a new auxiliary field. You can derive this action in various ways, using D-grains or using field theory techniques. What this field does for you is it lifts most of CPN and gives you just n isolated vacua on the vortex well sheet. So there's n isolated vacua. The vacua are given by setting sigma equal to 1 of the mi's, and then it's precisely that phi I. So you set sigma equal to 1 of the mi's, that makes one of these terms vanish. You're then allowed to turn on that phi I to cancel this r in the d term here. Okay? So without this term, CPN with this term, we've got some masses, and there's now just n isolated points on CPN. So if this is CPN, or CPN minus 1, then what this term has done for you is put on a potential with precisely n zeros. And the height of this potential is related to the masses. Okay, very good. So what's happened here is we've got n isolated vacua on the world sheet theory. These correspond to the n possible strings that we have. Okay, now comes the interesting point. We have a theory in 1 plus 1 dimensions, which is the theory on the string, that now has isolated vacua. But a theory in 1 plus 1 dimensions that has isolated vacua necessarily comes with a completely new type of particle. That is, I have the string over here, and I put it in vacuum 1, and as I move along, let me kink up and over on the world sheet one of these hills, and end up with a different type of string. So there's some object in the middle there, which is a kink, which in 1 plus 1 dimensions is a particle that can run up and down the string. So the question I want to ask is, what on earth is that kink? What does it correspond to in the 4-dimensional gauge theory? How do I think of this object? So let me tell you the answer. Ah, you're getting ahead. Yes. Okay, so now we have a kink. So there's a new type of object where we start with the first of these strings sitting in one of the vacua, which, well, let me put B star equals to 1 for now, which corresponds to a magnetic field up in the upper left-hand part. We have the kink, and then at the other side we sit in the other vacuum on the world sheet, which corresponds to the magnetic field sitting in the lower right-hand part, and what we want to figure out is what on earth is this object? How do we understand this? Well, let's look at the quantum numbers of this object. The quantum numbers are that it has to soak up this magnetic field and spit out this magnetic field. So what we see is that this object carries a magnetic field, but in the SU2 part of the U2, this is precisely the magnetic field carried by a Toff-Polya monopole. These are the magnetic quantum numbers Toff-Polya monopole. Let's compute the mass of the kink. Okay, the mass of the kink anywhere is essentially the distance it has to go in field space. Well, this distance is r, that's the size of the CPN, times the height of the barrier, which is m. Now it turns out there's a factor of 2 pi that comes in here, times r times m. But what's r? We saw yesterday that r is 2 pi over e squared. So this is 4 pi over e squared. But m is precisely the vacuum expectation value of that adjoint scalar A. And this is the mass of the magnetic monopole. Okay, so what's going on here? It carries the same quantum numbers as a magnetic monopole, it has the same mass as a magnetic monopole. We should probably begin to suspect that this object is really a magnetic monopole. How does this work? Well, think about what we've done. We started in the Seiberg-Witten theory with v squared equals 0. A bunch of U1 photons floating around. There's a magnetic monopole there. Its flux goes out radially with carrying its magnetic charge. Now we've turned on v squared. What happens as you turn on v squared? Well, the Higgs fields get a VEV, and they do what Higgs fields do, which is they invoke the Higgs mechanism, and the photons get a mass. Okay, so now you're sitting in the superconducting phase of this theory, and the Meissner effect kicks in. The magnetic flux can't propagate freely in the vacuum. What it does is exactly what it does in laboratory experiments and superconductors. It forms collimated flux tubes. So the magnetic monopole in Seiberg-Witten theory gets confined, the Joule confining mechanism, and its flux is now emitted in 2 collimated flux tubes. Those flux tubes are precisely the vortex string that we started with. Okay, so we sort of saw the magnetic monopole from the opposite perspective, starting with a vortex string and putting an excitation in the vortex string, which is the magnetic monopole. Okay, so this is a confined magnetic monopole. Yeah, go ahead. Yeah, in a superconductor, absolutely. Actually, in a superconductor, no, because it's a Cooper pair that forms, so it's charge 2e, and there it's not. But here, no, here it's a different reason. Here it's well, let me not tell you what it. But no is the answer. It forms. You see, this guy here has charge always in the Cartan subalgebra of the SU part. Okay, whereas the vortex strings that this theory admits always live in the U1 part of UN. So you can't build a vortex string in the theory that could carry this magnetic charge. It has to go out in two. And it's crucial, of course, because it means I've got a stable object. In fact, it's more than stable, as I'll now explain. It's actually BPS. Okay, so what we're witnessing here is just the Meissner effect. What's rather striking about this result is that the excitation above the vortex string has exactly the same energy as the monopole in free space. Okay, that's rather odd. You start with a monopole, you turn on v squared a little bit, the mass of the monopole does change. It changes by infinity because suddenly it's got to drag these infinite vortex strings with it. But nonetheless, the excitation energy above an infinite vortex string remains the same as it did before. So that's a little strange. That's because of supersymmetry. Okay, that's what the magic of supersymmetry is doing for us here. It's not allowing this kink, the mass of this kink or this monopole, to depend on v squared as we crank up v squared. Yeah. Yes. Good. So I can have different kinds of two-kink solutions. If I just have a single string here, then what I would need is at least 3 vacua, which means SU3. So if I have SU3 or SUN, I can start to put one monopole, then another monopole, then another monopole, up to n-1 of them. If I'm actually in SU2 and I want to put multiple monopoles here, I'm going to have multiple strings coming out. So I need to not consider the action for a single string, but the action for multiple strings, which can be done. Okay, so let me just draw a nice picture here. Okay, this is what the solution looks like from the 4D perspective. The size of the core of the monopole is 1 over m, that's the Higgs bed. The size of the flux tube here, you see at small distances it looks just like a Toff-Polyakov monopole. Things start to go out radially. At some point it realizes, oh, I can't do that, there's a mass for the photon, so it has to form collimated flux tubes, and it does that at a scale 1 over eV, which is the Higgs bed. As v goes towards 0, this thing smoothly goes out towards the Toff-Polyakov monopole. So let me just tell you something that's surprising, that surprised me, is that this configuration is a quarter BPS, meaning it preserves supersymmetries. What that means in practice is that you can take the first order equations of motion from this rather complicated Lagrangian and integrate them once to give first order Bogomolny type equations. Now I'm not going to show you how you do the Bogomolny completing the square trick, but it's not very hard. But we've seen in the last 2 lectures that you can take second order equations and integrate them once. These are some of the more complicated examples of that, where you can show these first order equations do indeed imply the second order equation. Notice they're kind of cute. The first 3, if you ignore this, are actually the equations for a Toff-Polyakov monopole. This one, and this one is the equation for a vortex string. And actually, it turns out these also admit domain wall solutions. Actually, they also admit D-brain solutions, but I won't tell you the full details. Okay, I should say that no analytic solution to these is known. It's not surprising because no analytic solution is known even for the infinite vortex. Okay, good. So far everything has been classical, but the real interest, of course, is in quantum theory. So the plan now is to tell you how you quantize this theory on the vortex string and how, again, it captures information about the Seiberg-Witten solution. So before I do that, are there any questions? You guys are just dead. Yeah, so this is the monopole. When V is 0, it has a particular mass. This, okay? When we turn V on, its mass jumps by infinity because now it's confined, it's not got an anti-monopole to meet, so its flux tube just have to go out. But if you consider an infinite flux tube and look at the excitation energy above that, that's finite, and that's equal to what the excitation energy was in free space in the Coulomb phase.
So if this is to say simply, there's a string sitting there, there's a monopole sitting on it, and they're happily sitting. Drag the monopole into the string, it'll turn on its own.
No, the monopole can't possibly be on its own in the Higgs phase, right? Because it's confined. No more than a core can be on its own in QCD.
You're only, I'm sorry, in the core it can't be house. I can have a monopole outside.
No, outside Q is non-zero. If you're in the Higgs phase, it's not possible. Yeah, the monopole is obliged to be attached to a string. It doesn't have any other option. It's the Meissner. Okay, so now let me tell you about the quantum theory. Okay, so the key point that I want to make is that the equation that M kink is equal to M monopole. This equation that I just derived classically over here. This survives in the full quantum theory when you quantize. Okay, Seiberg and Witten tell you how to compute this, and in fact, it's fairly easy to compute the mass of the kink. It's protected by supersymmetry, and I'll tell you exactly how that calculation goes shortly. Let me explain to you exactly what this means, why this is impressive. Suppose we're at weak coupling in the 4D theory. So weak coupling remembers that Vev of A, which is equal to the masses, is much greater than lambda QCD. Okay, so when you're at weak coupling, everything is semi-classical. You can just start doing conservative calculations to determine the mass. What's the mass of the monopole? Well, it's got some classical value, which is what I've written over there. It gets a one-loop correction. And then it gets an infinite series of instanton corrections, which you can calculate. So these are corrections from Yang-Mills instantons in 4 dimensions. Okay, you can compute the mass of the kink in 2 dimensions. It also gets a one-loop correction, but of course the one-loop calculation you're doing is with 2-dimensional momenta running around a loop, not with 4-dimensional momenta, but it agrees with the 4-dimensional calculation. Then this infinite series of instanton corrections also agrees, where you're doing a Yang-Mills instanton correction in 4 dimensions, but a worldsheet instanton correction in 2 dimensions. And term by term, these things. Okay, let me show you the first hint that there's some magic going on here. Oh, I should give you some references. So this was shown by me and Ami Hanani on the same day, Schiffman and Jung. And in fact, it relies very heavily on some previous work from the mid-90s by Nick. Okay, so the first hint that something's going on is that you can look at this relationship here. So remember, this was the 2D sigma model coupling, and this was the 4D gauge coupling. What's nice is that when you take into account quantum effects, both of these objects are on. The sigma model coupling is running 2 dimensions, gauge coupling is running 4 dimensions. We have enough supersymmetry so that that's a one-loop exact statement. And the beta functions for these two objects agree. That means that this classical relationship is preserved under a normalization group flow. So this is preserved under RG. The Bayer coupling gets this one loop correction. There's some UV scale divided by the running scale. This holds for both R and for 2 pi over E squared. Okay. For those of you who know these things, this NC is the NC of the CPN sigma model. Obviously, in the 4-dimensional theory, it's 2NC minus NF, but NF is equal to NC, so it's 2NC. There's generalizations of this for NF greater than NC as well. Okay, what this means is that they both hit strong coupling at exactly the same scale, so the lambda QCD that the 4-dimensional theory sees is the same as the lambda CPN that the 2-dimensional theory sees. That is the strong coupling scale where both objects get a mass gap. That's going to be important if you want the masses of the two theories to agree. Okay, so let me tell you how you understand quantum effects in this 2D theory. And in fact, this is a standard trick that you use that is common to many, many theories. I think it probably dates back to Gross and Levert, who were the first to use it. So let me explain this trick because it's useful time and time again when you're studying quantum theories, especially in low dimensions. So the theory on the vortex, as we've seen, is the CPN sigma model, which involves this as the bosonic terms. It now has this potential term that's giving us, making sure we only have those n isolated vacua corresponding to the magnetic field in the diagonal. It has a bunch of fermions. These are required by 2-2 supersymmetry and in fact fixed by 2-2 supersymmetry. There's a Yukawa coupling between the dynamical fermions and the sigma field. And then there's some constraints on the fermions that are superpartners of these constraints here. So you introduce these new non-dynamical fermions, zeta. Okay, so what do these guys do? If you were to integrate out these guys, or just treat them as Lagrange multipliers, you see that they tell you that the psi times the phi is 0. This means that you should think of these psi's as living in the tangent space of the CPN model. Okay, here's CPN. You pick some particular phi. This tells you that the fermions have to be tangent to that phi, which is exactly what fermions do in 2-2 sigma models. They live in the tangent space of the target space. Yeah. I've taken it to infinity because none of these things are dynamical. They're just there as auxiliary fields. Okay, so what do we have? We have some things we're obviously interested in, which are the phi's and the psi's. These are the things that are dynamical. And then we have a bunch of other guys which are just purely auxiliary. They're just there as artifacts to write down a simple linear expression instead of some complicated nonlinear sigma model. For example, the metric on CPN is the Fabini study metric, but I've never had to write down the Fabini study metric here. It's sort of encoded in all these auxiliary fields that we should really integrate out. So we have auxiliary fields. So what do we have? We have D, which is a real scalar. And we have this gauge field, U alpha. And we've seen several times that the D and the gauge transformation restrict the phi's to the CPN. We have a bunch of other guys. We have sigma, which is a complex scalar. So what does sigma do for us? Well, sigma does two things. Firstly, we've already seen that sigma was put in to generate this potential on CPN. But even if the masses weren't there, integrating out sigma would give, there's a sigma squared here, there's a term linear in sigma here. So it will give sigma equals 2 fermions, which when you put it back in gives a 4 fermion coupling. Okay, so sigma does two things. It gives us a potential and it gives us a 4 Fermi coupling. But again, always has to be there in supersymmetric sigma models. There's this Riemann tensor term times 4 fermions. And finally, we have some complex fermions whose role is simply to insist that the dynamical fermions live in the tangent space. Okay, so this is the trick that you should use over and over again, especially in low dimensions. You want to understand the quantum mechanics of this model. We know that R runs, things are going to become strongly coupled in the infrared. How are you going to understand this? What are the correct degrees of freedom? Well, you think you're interested in these guys, the phi's and the psi's. They were our dynamical varieties. But you're wrong. You're not interested in those at all. You're really interested in these auxiliary objects, which you just put in as a trick. But really, these are the guys that capture all the physics. Okay, so as I said, this is a trick, I think, first done by Gross and Verk, but is useful in many, many situations. So here's the deal. What you do is you say, let's give sigma a bev. Let's make sigma large. So we give sigma a bev. We give sigma a bev so that sigma minus mi in this case is big. The phi i's become heavy. Okay, they're massless in the original Lagrangian. The mi's are not there, they're massless. The sigmas become heavy. Sorry, the phi's become heavy. We then integrate out the phi's. This will generate an effective potential for sigma. It will also generate kinetic terms for all these objects. And we can then check if that effective potential indeed gives sigma a bev, and if it did, everything's nice and consistent, and we can carry on. Okay? So this is the trick that we use. So let's see how to do this, and in fact supersymmetry comes to our aid, because all of these auxiliary fields that I wrote down themselves form a supermodel. Okay. So the auxiliary fields live in a twisted chiral multiplet. Okay, so if you don't know what a twisted chiral multiplet is, it's more or less the same thing as a chiral multiplet. The supersymmetry algebra we're considering is the same as n equals 1 in 4 dimensions, and you know there you have chiral multiplets that you're allowed to integrate over half of superspace, holomorphic quantities to give you something supersymmetrically invariant. By the time you get down to 2 dimensions, if you want to integrate in a Lorentz invariant way, there's a second way you can integrate over half of superspace that's also Lorentz invariant. Because Lorentz invariance is less limiting. And so there's a second kind of chiral multiplet you can write down called a twisted chiral multiplet that up to a flip of 2U1R symmetries has all the same properties as the original. Okay, so think of this, if you don't know what a twisted chiral multiplet is, just as a chiral multiplet. And they fit together in the following way. Okay, so now we do this trick that I just told you about, where we integrate out all the guys we thought were interesting, but really turn out not going to be. That's the phi's and the cosi's. Okay, so we integrate out phi's and the psi's to generate an effective action for this twisted chiral multiplet sigma. The first thing we're interested in, of course, is the potential. It turns out the superpotential is one loop exact. That's what the power of supersymmetry is doing for us in this theory. So we get a superpotential, or actually a twisted superpotential, which is the following. This is the classical superpotential. Why is that? Well, if I integrate just the term linear in sigma over half of superspace, 2 thetas, what I'm going to pick out is this term here, the d minus I f01. You then add the complex conjugate, this disappears, and what you're left with is rd, which was the term that we had in the classical action. Okay. If you make this complex, you pick up a theta term for this guy here. Then there's the one loop correction. This is the one loop correction. This is a subtraction point. So there's a couple of things to note here. If you set the mi's to 0, this superpotential is of this term S log S, which is kind of a famous superpotential. It's the Veneziano-Yankelevich superpotential for n equals 1 super Yang-Mills. That was noticed way back by De Vecchia and company in 1978, I think, was the first time. So for years, people have sort of speculated that there should be some relationship between n equals 1 super Yang-Mills in 4D and the CP and sigma model in 2D. I don't think that relationship is quite as firm as this one I'm explaining here, about exact matching of mass spectra, for example. That's n equals 2 in 4D, not n equals 1. The other thing I just want to mention, for those of you who know these things, is that if I write down the following formula for this effective superpotential, this, it turns out, is the Seiberg-Witten curve of the original 4D theory. So if people know what the Seiberg-Witten curve is, this is how it's related to the 2D physics. It doesn't matter. Okay, so where are the vacua of this theory? So the vacua obviously sit at the critical points of the superpotential. Which, once you differentiate and then exponentiate, you get the following expression. So just as a check, suppose all of the masses are much bigger than lambda, that's when the theory is weakly coupled and we expect the classical result to exist. So we can essentially set lambda equal to 0, and the vacua are then just the sigma equals mi, which were the classical vacua theory. Okay. However, when the masses become comparable to lambda, those classical values for the vacua change rather radically. So we have this sigma space, which is a complex field. It was originally introduced as just an auxiliary field. Another language is it's the Coulomb branch of the CPN sigma. It's another language people use. And in this space are n vacua. And as you vary the masses, these vacua start moving around in this space in a way dependent on how you vary the masses. Okay. Now we have n vacua, we can look for kinks. So the kinks start in one vacuum and go to another vacuum, and, well, I maybe have time, but yeah, let me just skip it. Let me just tell you, and I can explain later if you're interested, that the mass of the kink. See, I know what the superpotential is exactly, but I don't really know what the kinetic terms are for sigma. Okay, they're much harder to compute. As always, the Kähler potential isn't corrected by supersymmetry. So you might worry that without knowing the kinetic terms for sigma, it's going to be very hard for me to compute the mass of any topological object like a kink. It turns out that for this particular kink, the kinetic terms doesn't matter what they are. The mass of the kink is always the same, and it's simply given by 2 times the difference in the value of the superpotential evaluated in the two different vacuums. So this is the superpotential. What I do is I differentiate it, I find the vacuum, and then go back and evaluate the superpotential in that vacuum. The difference between the values of the superpotential here and here is equal to the mass of the kink. Okay? So the calculation that you can do, and it's actually not very hard at all, is to prove that the mass of the kink in this theory, given in this way, agrees exactly as a function of the masses mi's, which are the vevs on the Coulomb branch, with the mass of the monopole as predicted by Simon. Okay, yeah. No. So in 4 dimensions, that's true, and the n equals 2 symmetry allows you to compute those kinetic terms, the pre-potential. In 2 dimensions, you have half the supersymmetry, so it's n equals 2, 2, but that's 4 supercharges, and so all you can calculate reliably is the superpotential, not the pre-potential. There's one last thing I want to tell you before we go for lunch. So this is a story from about 2 years ago. This is a story from just last fall. Not sure why I didn't think of this 2 years ago, because it's kind of obvious. The question is, what happens if I dial these masses so that these vacua move and start to coalesce? Okay, what happens if I put all of these vacua on top of each other? Clearly, one thing that happens is there's no kinks anymore. Their mass goes to 0. Okay, so the mass of a kink going to 0 is like the mass of a monopole going to 0. So it should be something interesting. So let's take the extreme case. If you set the masses equal to this, then all these vacua coalesce to n vacua sitting at the all sitting at the origin. Okay. So this is all sitting at sigma equals 0. So what happens? Well, what happens is kind of cute, actually. You plug this value for the masses, which you're free to choose, into the superpotential, and you see that all the branch cuts that come from these logarithms all cancel one another, and the logarithm disappears completely when you substitute in that value of the masses. And what you find is that the superpotential has an expansion as the leading order term is sigma to the n plus 1 plus some irrelevant operators. What's going on here is that the potential, which had a bunch of minima around each minima there was some mass for these oscillations. These were sort of quadratic minima. All of these guys are collapsing. And instead now, I guess it's sigma to the 2n, you have a much shallower potential that doesn't have a mass. What does this do? Well, this gives us conformal field theory in 2 dimensions. It's probably the simplest non-trivial conformal field theory in 2 dimensions. It has lots of supersymmetry. It's just the AN minimal model in 2 dimensions. Everything you could possibly want to know about it is not only known but very easy to compute. So you've got some conformal field theory living on the vortex world line. You could ask, what's going on up in 4 dimensions when we do this? Well, you can show that in the Seiberg-Witten theory, once you tune the masses to this particular value, that's sending yourself to a particular point on the Coulomb branch, the monopole becomes massless, as indeed it must. The kink became massless here. Not only that, some of the quarks become massless as well. And so you do sit in an interacting Argies-Douglas conformal field theory. The dimensions of all the chiral primary operators in the 4-dimensional conformal field theory match exactly the dimensions of all the chiral primary operators living on the string world sheet. So you have a nice map to talk to. Eva. No, the 4D theory is conformal on the Coulomb branch. But then you introduce this phi Heliopolis parameter and push yourself into the Higgs phase where everything has a mass gap. But then you put in a vortex, and inside the vortex, there's a little slice of the original Coulomb branch that now becomes a two-dimensional conformal field theory, not a 4D conformal field theory. So the size of the vortex is fixed by 1 over v squared. The four-dimensional theory in which the vortex lives is not conformal, but if you were to send v squared to 0, you hit a conformal field theory in 4 dimensions. Yeah, so it's not like a conformal field theory embedded inside a conformal field theory. It's kind of sitting above a conformal field theory in field space. Yeah. Sorry. Capital lambda? Oh, so lambda here is a dynamically generated. Sorry, I'm not sure I wrote this formula. R is the running via the opposite parameter. So this is lambda QCD. So lambda goes to 0 is really the same as saying mass is being much bigger than lambda, so I can just neglect quantum effects. But that's definitely not in this regime. This is mass is comparable to lambda. Sorry, you look confused now. Did I not? Yeah, I'm not. Why would you want to do that in this case? What physically would that mean? You're interested in situations where sigma is much larger than lambda? Sorry, I just didn't hear. Oh, right. Oh, I see. So this superpotential here, I think you can use that kind of discussion. In fact, this is fixed precisely by the symmetries, and I didn't put lambda in, but I could replace this subtraction point for a lambda, and then in the limit that went to 0, I'd be left with the classical term. So I think I could use that here. By the time I get to this superpotential, I'm deep in the quantum regime, so I definitely don't want to set lambda equal to 0. If I understood your question correctly, I think that's the right answer. Okay, I'm going to finish there. Thanks for your attention.